Okay. So getting started with our study guide here, we started with powers, and the first part of this was really just figuring out the vocabulary to talk about it. Instead of saying the big number and the small number, we had some actual names for it. The big number of an exponent we call the base. So in this case, that's the 5. The small number we call the exponent. In this case, that's the 3. And when we look at the entire thing stuck together, the 5 with the 3, we call that the power. This 5 to the power of 3 can be written in a couple of different forms. In exponent or power form, that is just 5 to the power of 3. There's not much else we can do there. We'll see how some things get interesting with negatives in a little bit. In expanded form, what this means is we're going to repeat the base, in this case 5, as many times as the exponent tells us to. So in this case 3. And the repetition is with multiplication. So we're looking at 5 times 5 times 5 as expanded form. And then standard form is really just the answer. Like what actually is 5 times 5 times 5. And again, in this unit, we do have calculators. So if you haven't pulled it out already, maybe take a moment and grab your calculator. So standard form, we type in what actually is 5 times 5 times 5, and we should be getting 125. This level of exponents and powers and repeated multiplication was theoretically covered in middle school. As we got to negative stuff, it is newer for grade 9. So this is where it started to jump into a bit more challenging things. So with negative powers, we can kind of, just by looking at them, we can see that there's different options here. We have the negative sign that's trapped inside of the brackets, and I call that a trapped negative. We have the negative sign that's just kind of floating outside the front. We call that a floating negative. We sometimes see some examples where it's a bit of both, and we have to figure out how to deal with that. Our goal is sometimes, essentially, we want to expand it first so that when we turn it back into standard form, we can see how the negatives interact with each other and stuff like that. So with a trapped negative, if the negative sign is trapped inside of the brackets, then the negative sign belongs to the base. So it's not just 4, it's negative 4. And it must be included in the repeated multiplication. So when we expand something like this, what we're going to say is we take the base, which is negative 4, and we multiply it by itself 3 times, because that's what the exponent says. So negative 4 times negative 4 times negative 4. And then we can look at pairs of negative signs that can cancel out. So we can take the first negative and cancel it with the second one, because 2 negatives, when we multiply them together, make a positive, which means that we are left with 1 negative sign overall. So that means that our answer, our standard form, our just regular basic number, will be negative. And then we just have to ask ourselves what actually is 4 times 4 times 4. Yeah, 64. There we go. Looking at the next one, same idea. Here we'll notice how it changes if we have an even exponent as opposed to a odd exponent. So this one here, when we expand it, we'll have negative 2 times negative 2 times negative 2 times negative 2. You'll notice in this one I didn't write the times sign. I just have the brackets kind of right up next to each other. That also implies multiplication. But we can still go through and cancel pairs of negatives. So this one can cancel with this one. And this one can cancel with this one, which means that our answer overall will be positive. We don't have to write the plus sign, but we can if we want to. Then we just have to decide what actually is 2 times 2 times 2 times 2. Yay, 16. Okay, when we have a floating negative, how I would usually approach this is really just look, so we have the negative chilling in the front, is we want to take all the stuff that's after that floating negative and figure out what that would be. And then we just slap a negative in front of whatever our answer is. So in this case, we're going to take this 3 to the power of 5, which is going to be 3 times 3 times 3 times 3 times 3. And then because we had this floating negative right in the front, we are going to float that negative in front of our expanded form. So we see that the negative only appears once. It doesn't appear with the 3 every time. And so now what we'll get is we have that negative sign and whatever 3 to the power of 5 actually is, which should give us 243. So this time our answer is negative overall. In this example here, we have a mix of a floating negative and a trapped negative. I would still approach this the same way that we did with the floating negative in the last one, to say, let's figure out what all of this stuff is, and then slap an extra negative in front of that. So we'll have -5, -5, -5. So that's -5 to the power of 3. But we have this negative right here. So we're going to slap that in front. And now we can use this negative when we start to cancel things out. So we can cancel out those two and those two, which leaves our answer as being positive. We just now have to decide what actually is 5 times 5 times 5, which we saw up here is 125. There we go. How are we feeling so far? Okay. Negatives definitely are where some things get weird, especially because when I'm marking questions like this on the test, the negative is really what I'm looking for. Like, hopefully we are definitely getting the actual number part as well, but I am definitely marking on whether or not you've decided this is positive 125 or negative. And if you have your negative wrong, you'll just get the question wrong. So it's not like, oh, I was halfway there. In this case, what I really am testing is whether or not you're putting plus or minus in front of it. So just be very careful of that on the test tomorrow. Okay, next up, we started getting into things, powers with base 10 and scientific notation. And both of these are really pattern-based. So we were able to expand a lot of things as we were learning it the first time. And we noticed some stuff. So if the exponent is positive, it means that it's a very large number. So in this case, anything that has a base of 10, we're looking at a bunch of zeros and a 1. And we just have to figure out in what order will these show up. The exponent will tell us the number of zeros after the 1. So this will be a really big number that will have 5 zeros after a 1. So we can write that out. So we've got our 1, and then we've got 1, 2, 3, 4, 5. Your calculator might choose to put commas in between every 3 things. You can do that. You can also choose to just kind of space it out a little bit. Sometimes I'll do that just to be able to count the zeros better. But really what we're looking at here is that we had 5 zeros because the exponent was 5. So we can take this as a really big number and go backwards and write it in exponent notation with a base of 10. Because we have a 1 and a bunch of zeros, we know it's going to be 10 to the power of something. And we're really just asking ourselves, what is that something? And again, the number of zeros is the exponent. So because we have 1, 2, 3, 4, 5, 6, 7, then it's going to be 10 to the power of 7. If, on the other hand, the exponent is negative, you'll have more details on this next year on how this works in kind of a different way. How we're approaching it this year is that a negative exponent will mean a very small number. So this will look something like 0 point, a bunch of zeros and then a 1, like we have here. We just have to decide how many zeros before the 1 shows up. And this one, it still is that the exponent is the number of zeros before the 1, but I put a couple of little stars here. We have to be extra careful where we're also including the 0 that shows up before the decimal point. So if we're saying -3, then that means that we're going to have 0, 0, 0, 1. But after that first 0, we're going to have our decimal. So it's not that we have 3 zeros between the decimal and the 1. We're including that one as well. So here our answer would be 0.001. So same idea, but going backwards is we can look at this and say, okay, how many zeros do we have here, including this front one? So we have 1, 2, 3, 4, 5, 6. So that means that our answer will be 10 to the power of -6. So the negative sign in an exponent like this implies that we're looking at a very small number, not that the number itself is negative. So it doesn't mean that we have negative 0 point whatever 1 or negative 10 to the power of -6. This just means that we're looking at a decimal number, whereas a positive exponent means that we're looking at a very big number. Any questions on that? Okay, the reason why we start with this is then leading into scientific notation involves powers with base 10. And it still follows the same rule of a positive exponent is a really big number, a negative exponent is a really small number. So here, what we are looking at is that we are moving the decimal as many times as the exponent tells us. So here it says 5.24 times 10 to the 6. So the decimal is between the 5 and the 24, and we are going to move it 6 spaces where any space that doesn't pass by an actual number will get filled with zeros. So I like to write this out as 524. So this is kind of the interesting part of the number. This just tells us some zero information. And we are moving the decimal from being between the 5 and the 2, as we see in the scientific notation here. And we're moving it 6 places. So one of the places goes past the 2, the next one goes past the 4, and then we have 4 other spots that need to be filled with zeros. So this is just a more efficient way to express this same number over here. So this would be considered standard form, whereas this is scientific notation. Same idea, but this time starting with our really big number and turning it into scientific notation, is we need to start by identifying what are the significant digits. In this case, it's the 1 and the 9 at the front here. But we always want to write that as the first digit, decimal, the next digit. So in this case, we would write 1.9. And if you're writing your test tomorrow and you forget how scientific notation should be written, you can always look back at another question that gives you scientific notation for a bit of a hint. So it reminds you about the decimal situation. It can remind us that we have times 10 to the power of something. We're just, again, wondering what that something is. Because it's a really big number, we know this must be positive. And so we're saying, okay, if the decimal is starting at the end of this number, we want to move it so that it is between the 1 and the 9, which would require going past 3, 6, 7, 8 numbers. So our exponent here will be 10 to the power of 8. Same idea, but with really small numbers. We're still talking about moving the decimal that many times. And the direction in which you're moving the decimal really depends if we're looking at a big number or a small one. So here, we're saying let's move that decimal 5 spaces this way, which means that the zeros will show up in front of the significant digits. So as we write this out, I would recommend taking this portion here and starting it at the end of your number, kind of giving yourself space for the zeros in front. And again, since the decimal in our scientific notation is between 8 and 7, it technically starts right here, but we want to move it now 5 places this way. One of the places brings us past the 8, so we have 4 more spots to go until we can actually write down our decimal. And any of those blank spots right there get filled in with zeros. Not forgetting the 0 in the front. So same idea. This one here, our significant portion of it, or our interesting digits, we only have one of them. We just have the 6 at the very end. So we can write this as either just 6 times 10 to the something, or if we want to, we can choose to write it as 6.0, just to kind of remind us that the decimal is moving from its spot over here to after the 6, just based on the notation, scientific notation. So then once again, we look at this and we say, okay, 3, 6, it goes past 9 digits in order to be right here. So we have a 9 at the end. But because this is a very small decimal number and not a very large number like what we saw up here, we know that this has to be a -9 instead. Okay. Looking at the front of this page here, do we have any questions? Okay. Well, then flipping it over, and what we have here are exponent rules. So the other day I handed you guys a white piece of paper that had all of the exponent rules. You will have that on the test. You will also have that eventually when we have our midterm. So those are never things that you have to memorize, but they are things that we have to remember how do they actually work. So here I will go through and write our general form rules as we go along here, just so that we know what we're working with. So for exponent of 1, our rule here is that a to the power of 1 is equal to a. And to be honest, this rule is even more helpful sometimes going backwards, to say that a base with no exponent means that the invisible exponent is 1. So sometimes that one can go backwards as well. In this case, all we're saying is that any base with an exponent of 1, the answer is just equal to whatever the base is. So here, our base is 8, and so our standard form is 8. Really, what we're thinking is it's 8 times itself only one time. So expanded form is it just shows up once. Here, our base is -2. So our answer is -2. -2 times itself one time. X to the power of 1 is equal to x. Where we have to be a little extra careful is these floating negatives, because here, remember with a floating negative, we really are thinking, okay, what is all of this stuff? And then slap a negative in front of it. So 4 to the power of 1 is 4, and we still have this negative hanging out, so we have to include that as part of our answer. But it still ends up just giving us -4. If we have an exponent of 0, our rule for this one, a to the power of 0 is 1. So a power with any base and an exponent of 0 is equal to 1. Again, we'll have to be careful with negatives, but that means 8 to the power of 0 is 1. -2 to the power of 0. So in this case, our base itself is negative, but we still get 1 overall. X to the power of 0 is 1. Our base is a variable, but it's still to the power of 0. Where we have to be careful is with this floating negative. Is we say, okay, 4 to the power of 0 is 1, but we have this negative sign out front, so we need to throw that in front of our answer. So what we're really looking at is -1. Any questions? These are also the ones, just be wary, on perhaps the test, perhaps the midterm, who knows, where I can kind of squish some things together. So I could say like x to the power of 0 plus 3 to the power of 1 times 8 to the power of 1. And we're following BEDMAS along the way. So just make sure that we're remembering that those types of questions exist. Next up, we have our product rule. So in math, product will always refer to things being multiplied. So our rule for this one is if we have two bases, or two powers, that are being multiplied together, whether that multiplying is with dot multiplication or the actual little x in the middle, what we want to do is add the exponents. And so we saw in our notes how this works when we expand it, so we kind of trust that the rule is valid. But it's just as easy as making sure that the bases match. So we have 3 and 3, and then we go, okay, then let's add the exponents. So 4 plus 7 will end up giving us the power 3 to the power of 11. So the base stays the same, the exponents add together. In this case, our base is p, so we can join those together. This is one of those examples where we don't have an exponent here, and so we have to remember that the invisible exponent is 1. But then we say, okay, this will be p to the power of something, and that something is whatever 3 plus 2 plus 1 is, which is 6. We'll see some examples in a bit where if we had different variables, how we handle that. Next up, we go to the power rule. We learned the quotient rule next, but this one's easier, so we're going to do that first in our study guide. The rule for this one is if we have a to the power of m to the power of n. So if it looks in this form where we have an exponent or a power with an extra exponent on the outside, it tells us to multiply the exponents. And again, we expanded this in our notes to really see why we're able to do that. But what that means for us here is we can just see, okay, we've got kind of an exponent on an exponent. And so this will end up being 3 to the power of whatever 4 times 2 is, which is 8. The next one, we have an exponent on an exponent on an exponent, but we can still just multiply them. We can say n to the power of 2 times 3, which is 12. The one thing that we do want to be careful of, and these ones have pretty big numbers, but if we have a numerical base, we can actually evaluate that. And as part of your final answer, you would want to on the test. So in this case, we can actually say, what is 3 to the power of 11? And if you have one of my boring calculators right now, maybe skip it for the moment. Typing in 11 times might be a lot, but what we get is 177,147. My goal is on the test to just double check it tonight to make sure that they're decently small enough exponents that if you're using a simple calculator, it should be okay. 3 to the power of 8, so 3 times 3, 8 times, we get 6,561. So anytime that we have a number as the base, we want to actually handle it instead of if we have a variable, that's as far as we can go. The quotient rule, this one has 2 parts to it, kind of really depending on if your exponent is higher on the top or the bottom. But in either case, what we're really thinking is that if we have a to the m over a to the n, sorry. Then our first step is always subtracting the exponents, but then you have to decide, will it live on the top or bottom? I'm just going to keep to that rule right now, even though we technically have a second version on our little sheet. We're really thinking subtract them. So we look at this, and again, we can only do this with bases that match. So we have 2 to the power of 12 over 2 to the power of 5. And so what we're able to say is, okay, what is 12 minus 5? That'll give us 7. And then that 7 will be left with 2 to the power of 7. And we're deciding that that's going to be on the top because that's where we had more of our exponents. When it's on the top, we really just don't have to write anything else. Essentially, we're assuming that the bottom is 1, but we don't have to write that. So on the top is just like our normal line of math. If it ends up on the bottom, like this one, so we have 10 W's on the bottom and 3 W's on the top, subtracting the exponents would leave us with W to the power of 7. But because we have more on the bottom, our W to the power of 7 is on the bottom of a fraction, which means that we need a 1 on the top as a placeholder. If we have multiple variables involved, so here we have A's and B's, here we have X's and Y's, we can only subtract the exponents of things that match. So for this one, we can say A to the power of 6 and A to the power of 8. When they battle each other out, we'll have just 2 A's left on the bottom. So we can set that up. When we look at the B's and when they battle each other out, remember that we have B to the power of 1 on the bottom. So we'll have 3 minus 1 left over, which is B to the power of 2 on the top. And then this is as far as it can go. There's nothing else we can do here because we can't join together the A's and the B's. In this one here, what we'll notice is a little bit different, is in both the cases of the X and the Y, the higher exponent is on the top, which means just everything will live on the top of the fraction, and that's okay too. So we do the same thing. We say, okay, 10 x to the power of 10 over x to the power of 8 will leave us with x to the power of 2 on the top. And then y to the power of 7 over y to the power of 2 will leave us with y to the power of 5 on the top, subtracting those exponents. And that's it. There's nothing on the bottom. We're just left with it on our like regular level of math. And we're almost there. You guys are doing great. Any questions so far? Okay. Looking at the distributive property here then, this is the idea of Oprah giving everyone a car. So what we get is our rule for this one, also on our sheet here, is if we have A over B with an exponent on the outside, that exponent gets distributed to everything on the inside. Or if we have A times B on the inside with an exponent on the outside, again, the exponent gets distributed. So we'll have A to the power of n times B to the power of n. So each time we're just looking at, okay, you get an exponent and you get an exponent, or you get an exponent and you get an exponent. So same thing here. We're saying, okay, you get a 9 and you get a 9. So our answer would be x to the power of 9 over 2 to the power of 9. Again, with the 2 being on the bottom there, we can actually evaluate it to say x to the power of 9 over 512. For this one, distributing the exponent through, we'll end up with 4 to the power of 7 times x to the power of 7. They just each get a power of 7. And again, we can go through and say what actually is 4 to the power of 7. Again, these are larger if you've got a simple calculator, I'm sorry. We get 16,384 times x to the power of 7. If we look at this and we see that there's kind of more going on inside of those brackets, we have a power within a fraction within some brackets that has a power. What we're looking at is distributing this to every part in the brackets. So here, the 3 different parts that we have are a, 4, and b squared. And so our intermediate step is that we can distribute the 3 to everything in there. So we have a to the power of 3, 4 to the power of 3, and we have b squared to the power of 3. But what we'll start noticing as we do this enough is that the 2 and the 3 here are now looking at a power rule, just like we saw up here, where now we have to multiply these exponents. And so there's nothing we can do to simplify the a to the power of 3. That'll stay there. We can simplify 4 to the power of 3. That'll give us 64. And then we can say, okay, b to the power of 2 to the power of 3 can multiply together to give us b to the power of 6. And so if you want, you can skip the step where you're really showing this and go straight to multiplying those two exponents, knowing that it's going to happen if you feel comfortable with that. So that means that for this one, we can take this exponent of 2 and distribute it to each part in the brackets, where we have a 3, we have m to the power of 5, and n to the power of 3. So distributing that through, we'll get 3 squared, which if you're feeling extra strong about this, we can go straight to being a 9. Then distributing the 2 to m to the power of 5, we'll end up with m to the 5 to the 2. So we can multiply those two things together to get m to the power of 10. And then same idea, we can get n to the power of 6, because we can multiply the 3 and the 2. Any questions? Okay, our last section here is the combined exponent rules, where we're taking all of those rules that we've talked about before and now joining them together in these kind of super fractions, lots of exponents, things going on. The goal here is that we want to simplify the numerator and denominator separately if possible. Then we simplify them together, so up and down when they go to battle, and then distribute the outer exponent. Our final steps will always be evaluating numerical bases if possible. So something like this, we want to look at this and say, okay, is there anything I can do to the top of this fraction to simplify it at all? And there's nothing we can do there. So then we say, okay, on the bottom, is there anything I can do to simplify this at all? And there's nothing we can do. So then we can say, okay, is there anything we can do to simplify up and down? And if there's two numbers, we actually haven't seen this too much. If we could simplify them like a regular fraction, we would. But in this case, 3/8, there's nothing we can do there. So those can stay. But we can simplify a to the power of 2 and a to the power of 5. And so setting up our new fraction here, the 3 and the 8 can stay. We'll end up with a to the power of 3 on the bottom, because we could cancel those two out, subtracting the exponents like we did before. And we can simplify our b's together, so b to the power of 7 over b to the power of 1 will give us b to the power of 6. We still have this big exponent on the outside. We can't forget about that from the start, or the first step here. But now the inside of the brackets are fully simplified. So now we can go through, and each of the things in the brackets can get the exponent of 2, just like we saw in the last step, or in the last type of question. So now we can say, okay, this 2 goes to the 3, so we get 3 to the power of 2. The 2 goes to the b to the power of 6, so those will end up multiplying to give us b to the power of 12. The 2 will go to the 8, so we get 8 squared. And the 2 will go to the a cubed, so again, those will multiply and give us a to the power of 6. And our last step is now just to say, okay, what actually is 3 to the power of 2? What actually is 8 to the power of 2? And so those will turn into 9, b to the 12, 64, a to the 6. And these definitely are complex looking questions, but what we're looking for at the end for something to be fully simplified is we have one of each base with whatever exponent it needs to be. There's no brackets left around it, and that's as far as we can go. Any questions there? Okay, then our very last one. This one doesn't have any super exponent on the outside, so it really just means that we simplify the top and the bottom on their own. So looking at the top in this green section, what rule can we use to simplify this? The power rule. So because we have an exponent on an exponent, we know that this will turn into x to the power of 4. Now looking at the bottom, I want you to be extra careful here. So notice that there are no brackets around this 3x to the power of 2. This means that the x is only, or sorry, the 2 is only attached to the x, and it has no relationship to the 3. Even though there's no dot right here, Remember, anything that's just stuck together like that is implied multiplication. So if you want to put a dot in between, you can. But what we're looking at is we have 3 to the power of 1 times x to the power of 2 times 3 to the power of 2 times x to the power of 3. So we can bring together these two things. So that'll give us 3 to the power of 3 on the bottom. We can also bring together the x's on the bottom to get x to the power of 5. And now the top and bottom are as simple as it gets. There's nothing we can do here. There's nothing we can do here. But what we can do is simplify x to the power of 4 and x to the power of 5. Subtracting those exponents will leave us with 1x on the bottom because that's where we had more x's. And so here we actually lose everything from the top. And so when we lose everything from the top, we have to put a 1 there. 3 to the power of 3. And just a singular x at the bottom when we canceled those out. And our last step here is we can say what actually is 3 to the power of 3. And in this case, I'm going to be a touch lazy and just erase it and replace with 27. So we started with a pretty complex thing with a bunch of x's and quite a few 3's. And we're left with only 1x at the bottom here. Notice at the bottom that I say plus geometry and problem solving. A lot of times on these study guides, we don't have kind of the space to go through those types of questions, but all of them are using skills that we've covered on this entire thing. So if you want to, my recommendation is I will hand out a practice test in just a moment. I would probably start with the ones that you feel most uncomfortable with, just to make sure you have the time to get through stuff that like you might want to ask questions for. Whereas you'll see at the start of the practice test is a bunch of this kind of stuff, which I think by now is what you're mostly feeling good about. So don't just start with what you feel good about, even though that makes you feel more confident, because it might be false confidence. So just when you get your study guide in a second here, you'll